US Physics Olympiad year 2011 USAPHO Semifinal exam. This exam consists of 2 days, each day for 60 minutes. First day there were 4 problems, which was part A, and the second day was 2 problems, part B. Problem A1. Solutions for all problems you can find below this video in the reference of the description. Single bubble sonoluminescence occurs when sound waves cause a bubble suspended in a fluid to collapse so that the gas trapped inside increases in temperature enough to emit light. The bulb actually undergoes a series of expansions and collapses caused by the sound wave pressure vibrations. We now consider a simplified model of a bubble undergoing sonoluminescence. Assume the bubble is originally at atmospheric pressure E0 equal 101 kilopascal. When the pressure in the fluid surrounding the bubble is decreased, the bubble expands isothermally to a radius of 36 microns. When the pressure increases again, the bubble collapses to a radius of 4.5 microns, so quickly that no heat can escape. Between the collapse and the subsequent expansion, the bubble undergoes isochoric constant volume cooling back to its original pressure and temperature. For a bubble containing a monatomic gas suspended in water of temperature T equal 293 Kelvin, find A. The number of moles of gas in the bubble, B. The pressure after the expansion, C. The pressure after collapse, D. The temperature after the collapse, and E. The total work done on the bubble during the whole process. You may find the following useful. The specific heat capacity at constant volume is CV equal 3/2R. The ratio of specific heat at constant pressure to constant volume is gamma equal 5/3 for a monatomic gas. US Physics Olympiad year 2011 USAPHO Semifinal exam. Problem number A2. Solution for this problem you can find below this video in the reference of the description. A thin uniform rod of length L and mass M equal 0.258 kilograms is suspended from a point a distance r away from its center of mass. When the end of the rod is displaced slightly and released, it executes a simple harmonic oscillation. The period T of the oscillation is timed using an electronic timer. The following data is recorded for the period as a function of R. What is the local value of G? Do not assume it is the canonical value of 9.8 meters per second square. What is the length L of the rod? No estimation of error in either value is required. The moment of inertia of a rod about its center of mass is 1/12 mL square. You must show your work to obtain full credit. If you use graphical techniques, then you must plot the graph. If you use linear regression techniques, then you must show all of the formulae and the associated working used to obtain the results. These are experimental data here. US Physics Olympiad year 2011 USAPHO Semifinal exam. Problem A3. Solution for this problem you can find below this video in the description reference. A light bulb has a solid cylindrical filament of length L and radius A, and consume power P. You are to design a new light bulb using a cylindrical filament of the same material, operating at the same voltage, but emitting the same spectrum of light, which will consume a power Np. What are the length and radius of the new filament? Assume that the temperature of the filament is approximately uniform across its cross-section. The filament doesn't emit light from the ends, and energy loss due to convection is minimal. US Physics Olympiad year 2011 USAPHO Semifinal exam. Problem A4. Solution for this problem you can find below this video in the reference of the description. In this problem we consider a simplified model of the electromagnetic radiation inside a cubical box of side length L. In this model the electric field has a spatial dependence E as a function of x, y, z equal this expression, where one corner of the box lies at the origin of the box is aligned with the x, y, and z axis. Let h be Planck's constant, k be the Boltzmann's constant, and c be the speed of light. Question A. The electric field must be zero everywhere at the sides of the box. What condition does this impose on kx, ky, and kz? Assume that any of these may be negative and include cases where one or more of the ki is 0, even though this cause E to be 0. Question B. In the model, each permitted value of the triple kx, ky, kz corresponds to a quantum state. These states can be visualized in a state space, which is a notional three-dimensional space with the axes corresponding to kx, ky, and kz. How many states occupy a volume S of the state space if S is large enough that the correspondences of the states can be ignored? Question C. Each quantum state in turn may be occupied by photons with the frequency omega equal f over 2 pi equal c multiplied by model k, where c is speed of light and k is length of vector k in this space. If the temperature inside the box is T, no photon may have energy greater than kBT, where kB is Boltzmann constant. What is the shape of the region in state space corresponding to occupied state? Question D. As a final approximation, assume that each occupied state contains exactly one photon. What is the total energy of the photons in the box in terms of H, KB, C, and T, and the volume of the box? Again, assume that the temperature is high enough that there are a very large number of occupied states. Hint: divide state space into thin regions corresponding to photons of the same energy. Note that while many details of this model are extremely inaccurate, the final result is correct except for a numerical factor. US Physics Olympiad, year 2011, USAPHO, Semifinal exam. Problem B1. Solution for this problem you can find below this video in the description reference. An AC power line cable transmits electrical power using a sinusoidal waveform with a frequency 60 Hz. The load receives an RMS voltage of 500 kV and requires 1000 MW of average power. For this problem, consider only the cable carrying current in one of the two directions and ignore effects due to capacitance or inductance between the cable and with the ground. Question A. Suppose that the load on the power line cable is a residential area that behaves like a pure resistor. 1. What is the RMS current carrying in the cable? 2. The cable has a diameter 3 cm, is 500 km long, and is made of aluminum with a resistivity 2.8, 10 power negative 8 ohm by meter. How much power is lost in the wire? Part B. A local rancher thinks he might be able to extract electrical power from the cable using electromagnetic induction. The rancher constructs a rectangular loop of length A and width B less than A, consisting of n turns of wire. One edge of the loop is to be placed on the ground. The wire is straight and runs parallel to the ground at height h, much less than the length of the wire. Write the current in the wire as a function of omega t in form of I0 sine omega t, and assume the return wire is far away. First, determine an expression for the magnitude of the magnetic field at a distance r from the power line cable in terms of I and r and the fundamental constants. 2. Where should the loop be placed and how should it be oriented to maximize the induced EMF in the loop? 3. Assuming the loop is placed in this way, determine an expression for the EMF induced in the loop as a function of time in terms of any of all these parameters and the fundamental constants. 4. Suppose that A equal 5 meters, B equal 2 meters, and H equal 100 meters. How many turns of wire N does the rancher need to generate an RMS EMF of 120 volts? Part C. The load at the end of the power cable changes to include a manufacturing plant with a large number of electric motors. While the average power consumed remains the same, it now behaves like a resistor in parallel with a 0.25 Hz inductor. First, does the power lost in the power line cable increase, decrease, or stay the same? You need not calculate the new value explicitly, but you should show some work to define your answer. 2. The power company wishes to make the load behave as it originally did by installing a capacitor in parallel with the load. what should be its capacitance. US Physics Olympiad, year 2011, USAPHO. Semifinal exam. Problem B2. Solution for this problem you can find below this video in the reference of the description. A particle is constrained to move on the inner surface of a frictionless parabolic ball whose cross-section has equation z equal kr square. The particle begins at height z0 above the bottom of the ball with a horizontal velocity v0 along the surface of the ball. The acceleration due to gravity is g. Question A. For a particular value of horizontal velocity v0, which we will name vh, the particle moves in a horizontal circle. What is vh in terms of g, z0, and or k? Question B. Suppose that the initial horizontal velocity is now v0 greater than vh. What is the maximum height reached by the particle in terms of v0, z0, g, and or k? Question C. Suppose that the particle now begins at height z0 above the bottom of the ball with the initial velocity v0 equal 0. First question. Assuming that z0 is small enough so that the motion can be approximated as a simple harmonic, find the period of the motion in terms any or all of the masses of the particle m, g, z0, and or k.